Hello everyone, welcome back to Interview Breaker. In today's video, we're diving into a fundamental topic for iOS developers. Where in memory are value types and reference types stored? Understanding how value types and reference types are stored in memory is crucial for writing efficient and high-performance applications. This knowledge helps you make informed decisions about data structures, memory management, and the overall architecture of your app. So let's delve deep into the intricacies of memory allocation for value types and reference types in Swift, the primary language used for iOS development. Before we explore value and reference types, it's essential to understand the two primary regions of memory where data is stored. First one is stack memory and the second one is heap memory. Stack memory is a region that stores temporary variables created by functions. It's organized in a last in first out LIFO manner, making allocation and deallocation extremely fast and efficient. Heap memory, on the other hand, is used for dynamic memory allocation. It's a larger pool where objects are stored and can be accessed globally. Allocation and deallocation here are comparatively slower due to the overhead of dynamic memory management. Value types. In Swift, value types are data types where each instance keeps a unique copy of its data. Modifying one instance doesn't affect others. Examples of value types: structures, enumerations, tuples, basic data types like int, float, double, bool, and string. Yes, string is a struct in Swift. Value types are typically stored on the stack. However, it's important to note that the Swift compiler is optimized to handle value types efficiently, and under certain circumstances it may allocate them on the heap. But generally, for our understanding, value types are associated with stack memory. Characteristics: fast access. Stack allocation allows for quick access and deallocation as the memory is managed predictably. Automatic memory management. Memory for value types is automatically allocated and deallocated when they go out of scope. Copy semantics. Assigning a value type to a new variable or passing it to a function creates a copy of the data. In this example you see on the screen, point A and point B are separate instances with their own copies of data. Reference types. Reference types are data types where instances share a single copy of the data, and modifying one instance affects all references. Examples of reference types: classes, functions and closures, Objective-C types. Reference types are stored on the heap. The heap allows for dynamic memory allocation, which is necessary for reference types that can be accessed from various parts of the code. Characteristics: dynamic memory management requires careful management to avoid memory leaks. Swift uses automatic reference counting (ARC) for this purpose. Shared instances. Multiple variables can reference the same instance. Reference semantics. Assigning a reference type to a new variable or passing it to a function shares the same instance. Here in that example, changing person B name also changes person A name because both variables reference the same instance. Memory allocation nuances. While the general rule is that value types are stored on the stack and reference types on the heap, in practice, the Swift compiler performs optimizations that might blur these lines. Escape analysis. The compiler analyzes whether a variable escapes the scope in which it's defined. If a value type is large or escapes its scope, the compiler might allocate it on the heap to optimize performance. Performance considerations. Value types, ideal for small, frequently used data structures. Stack allocation and deallocation are faster. Predictable behavior due to copy semantics. Reference types, suitable for complex data structures that need to be shared across different parts of the app. Heap allocation incurs overhead, requires careful memory management to avoid retain cycles. Memory management, best practices. Avoid retain cycles. Use weak or unowned references where appropriate. Be cautious with closures capturing self. Choose the right type. Use structs for simple data models that don't require inheritance. Use classes when you need reference semantics or to inherit behavior. Understanding scope and lifetimes. Variables on the stack are deallocated automatically when they go out of scope. Heap allocations persist until all references are released. Be mindful of long-lived references that can lead to increased memory usage. Let's look at some practical examples. Using value types for thread safety. Since value types are copied when passed around, they're inherently thread safe. Modifications in one thread do not affect copies in other threads. Managing reference types in multi-threaded environments. Access to shared reference types must be synchronized to prevent race conditions. Use synchronization mechanisms like locks, serial queues, or thread-safe data structures. Let's talk about some advanced topics. Escaping closures and memory capture. closures can capture variables from their surrounding context. If a closure escapes its defining scope, captured variables are stored on the heap. The escaping keyword indicates that the closure may outlive the function scope. Structs with reference type properties. Even though a struct is a value type, if it contains reference type properties, the reference semantics apply to those properties. Conclusion. Understanding where value types and reference types are stored in memory is crucial for efficient iOS development. Here's a recap. Value types stored on the stack generally, fast allocation, deallocation, copied when assigned or passed to a function, used for simple, immutable data structures. Reference types stored on the heap, shared instances across multiple references, managed through ARC, used for complex, mutable objects that need to be shared. Key takeaways for developers. Choose value types for data that benefits from copying and isolation. Opt for reference types when you need shared mutable state. Be mindful of memory management practices to prevent leaks and optimize performance. Understand how Swift's compiler optimizations might affect memory allocation. By leveraging this knowledge, you can write more efficient code, prevent common pitfalls related to memory management, and ultimately create better performing iOS applications. You definitely know someone who would benefit from this content. Feel free to share it with them, and if you found this video helpful, please give it a thumbs up and subscribe to Interview Breaker. Thanks for watching, and I'll see you in the next video.